When we think about nuclear power, we often picture the immense energy it produces, lighting up entire cities and powering industries. But have you ever wondered what happens to the fuel that powers a nuclear reactor once it's used up? The story doesn't end when the lights turn on. Imagine the ash left behind after a campfire burns out, except this ash is no ordinary residue. It's intensely radioactive, glowing with energy, and it remains hazardous for thousands, even tens of thousands of years. Unlike campfire ashes, you can't simply sweep it away or scatter it in the wind. Nuclear power is celebrated for generating vast amounts of clean, carbon-free electricity, helping to fight climate change and reduce air pollution. But behind this promise lies a significant challenge: the management of its dangerous waste. This isn't just ordinary trash you can throw out with yesterday's leftovers. It's radioactive, emitting invisible but deadly rays, and must be handled with the utmost caution and expertise to protect people and the environment. Some forms of nuclear waste remain hazardous for periods longer than the rise and fall of entire civilizations. Imagine waste that will still be dangerous when today's cities are ancient ruins and new societies have risen in their place. Storing this waste safely isn't just a technical problem, it's a moral responsibility. We owe it to future generations to ensure they aren't burdened by our energy choices today. You can't just toss nuclear waste in a landfill or bury it in your backyard. It needs to be shielded from the environment, cooled to prevent overheating, and constantly monitored to ensure nothing goes wrong. Right now, most nuclear waste is stored on-site at power plants, either submerged in deep pools of water or sealed inside thick concrete and steel dry casks. These methods are safe for the short term, but they're not designed to last forever. Think of these storage solutions like keeping leftovers in your fridge. They're fine for a while, but eventually, you need a better plan before things go bad. The ultimate goal is to process, reduce, and find a permanent home for this waste, one that will keep it isolated from people and the environment for as long as it remains dangerous. For decades, scientists and engineers around the world have been searching for a solution that can stand the test of time, something that will keep radioactive waste safely contained for thousands of years. The challenge is immense: to design a system so robust, so secure, that it can be trusted to protect life on Earth for an almost unimaginable length of time through natural disasters, climate changes, and even human forgetfulness. For years, the world has been in a holding pattern, waiting for a breakthrough, a way to move beyond temporary fixes and finally solve the nuclear waste puzzle. But now, a simple yet powerful scientific innovation may be on the horizon. This new approach could change everything we know about nuclear waste management. And that's where our story begins. A journey into the heart of one of humanity's most glowing problems, and the search for a solution that could shape our future for generations to come. Storing spent nuclear fuel is a slow, painstaking, and costly process, and that's entirely by design. The stakes are high, and every step is engineered for maximum safety and security, not speed. When it comes to nuclear waste, there are no shortcuts. Right after use, nuclear fuel is incredibly hot, both in terms of temperature and radioactivity. To prevent dangerous radiation from escaping, these fuel rods are immediately placed in deep pools of water. The water acts as both a coolant and a shield, absorbing radiation and keeping workers and the environment safe. This cooling off period isn't short. Spent fuel can remain in these pools for 5 to 10 years, sometimes even longer, until it's safe enough to handle. The process is slow, but it's essential for reducing the risk of overheating and radiation leaks. Once the fuel has cooled sufficiently, it's carefully transferred into massive dry casks. These are like steel and concrete fortresses, engineered to withstand earthquakes, floods, and even direct impacts. They're designed to keep the radioactive material contained for decades, if not centuries. But these casks come at a high price. Each one is expensive to manufacture and maintain, and as more nuclear fuel is used, more casks are needed. Power plants around the world are running out of space to store them. The ultimate goal is to find a permanent solution, like burying nuclear waste deep underground in stable geological formations. This would isolate the waste for thousands of years, far away from people and the environment. However, finding a site that's both geologically stable and publicly acceptable has proven incredibly difficult. Political, environmental, and social concerns have led to decades of delays and unfinished projects. In the meantime, scientists are working on reprocessing, chemically separating spent fuel to recover usable uranium and plutonium. This process can recycle valuable materials and reduce the volume and toxicity of the waste that needs to be stored. Reprocessing helps shrink the storage problem, but it's a complex, expensive, and energy-intensive process. Making it more efficient and cost-effective is a major challenge for the industry. The real challenge is to develop new technologies that make nuclear waste processing faster, cheaper, and even safer, without compromising on security or environmental protection. Every small improvement in storage, handling, or processing brings us a step closer to a long-term solution. It's a marathon, not a sprint, and progress is measured in years, not days. But the pace is picking up. New ideas, advanced materials, and innovative engineering are changing how we think about nuclear waste management. The future of nuclear waste management will depend on breakthroughs in processing, storage, and recycling. Breakthroughs that could make nuclear energy safer and more sustainable for generations to come. And one such breakthrough, a new nuclear alloy, is already making waves in the industry. Let's see how it could change the game. At the sprawling Savannah River site in South Carolina, a team of dedicated scientists and engineers faced a surprisingly stubborn challenge, one that threatened to slow down the entire nuclear cleanup process. Their task was to dissolve decades-old nuclear fuel rods, which were made from a particularly tough aluminum alloy. These rods, relics from research reactors, had to be safely broken down in order to process and store the radioactive material inside. The standard method involves submerging the fuel rods in a powerful acid bath, a process designed to dissolve the metal and free the nuclear material for further handling. But the alloy in question, known as 6061, was engineered for strength and corrosion resistance. It was so durable that it stubbornly resisted the acid, refusing to break down at the expected rate and causing major delays. This slow reaction didn't just waste time, it also led to the production of extra chemical waste, as more acid and resources were needed to try to dissolve the alloy. The entire cleanup process became less efficient, creating bottlenecks and logistical headaches. Imagine trying to wash a mountain of dishes coated in superglue. No matter how hard you scrub, progress is painfully slow, and the dirty dishes just keep piling up. That's what it felt like for the team at Savannah River. As a result, more and more fuel rods stacked up, waiting for their turn in the acid bath. The facility's storage areas grew crowded, and the backlog threatened to overwhelm the site's capacity. Cleanup timelines stretched further into the future, and the costs of managing the waste and delays began to soar, putting pressure on both budgets and schedules. The team knew they needed a breakthrough, a way to break through this chemical logjam and restore efficiency to the cleanup process. They gathered to brainstorm, determined to find a solution. Surprisingly, the answer wasn't to use a stronger acid or harsher chemicals. Instead, the solution lay in developing a smarter, more innovative material that could work with the process, not against it. That's where innovation stepped in, paving the way for a new chapter in nuclear cleanup at the Savannah River site. The breakthrough came from rethinking the material itself. Instead of fighting the stubborn alloy, scientists designed a new aluminum alloy that dissolves easily after its job in the reactor is done. By tweaking the recipe, adding a bit of bismuth, they created a strong yet cooperative alloy. In tests, it dissolved much faster and more completely than the old version. The process became smoother, more predictable, and efficient, like dissolving a sugar cube instead of a rock. This simple change didn't require new factories or futuristic tech. The new alloy can be used for future fuel, making disposal easier from the start. Even legacy fuel can benefit, as the discovery informs new cleanup strategies. Sometimes, the smartest solution is the simplest. This new alloy speeds up nuclear waste processing dramatically. Faster dissolving means the Savannah River site can handle more fuel in less time. This acceleration could cut decades off the cleanup schedule, saving taxpayers millions. Fewer chemicals are needed, reducing secondary waste and environmental impact. The process is safer, greener, and more cost-effective. Facilities can now process larger volumes, boosting national capacity. This innovation isn't just about efficiency. It's about building confidence in nuclear energy's future. Smarter waste management makes nuclear power more sustainable. A small change in materials science is transforming the entire system. The ripple effects are enormous. This breakthrough changes the landscape of America's nuclear legacy. Spent fuel is stored at dozens of sites nationwide, each requiring security and oversight. The new alloy makes centralized processing and permanent storage more feasible. Fewer sites mean less risk and a lighter burden on local communities. Public trust grows when people see real progress, not just promises. Accelerating cleanup fulfills our responsibility to future generations. We're not just saving money, we're protecting the environment. 21st century science is solving 20th century problems. The nuclear waste challenge is global, and every country is searching for solutions. France leads in reprocessing, recycling spent fuel to reduce waste. Russia and China are developing fast reactors that burn long-lived waste, turning problems into resources. Finland and Sweden are building deep geological repositories, setting global examples for safe, permanent storage. The US alloy breakthrough fits into this tapestry, making reprocessing faster and repositories smaller. There's no single answer. Innovation is happening on many fronts. Each breakthrough adds a new tool to the global effort. The world is learning from each other, moving closer to a sustainable solution. Progress is a team effort. Solving nuclear waste isn't just about cleanup. It's about unlocking clean energy's full potential. Nuclear power is reliable and carbon-free, but waste concerns have slowed its growth. Every step toward better waste management makes nuclear energy more attractive. This breakthrough shows real, practical progress, right now. Advanced reprocessing and recycling can make nuclear almost fully sustainable. The new alloy is a key piece of that puzzle. With smarter waste solutions, nuclear can anchor a resilient, carbon-free grid alongside renewables. The future of clean energy depends on solving the waste challenge, and we're getting there. The new alloy at Savannah River is a story of hope and human ingenuity. For years, nuclear waste felt like an unsolvable burden. This breakthrough proves we're not stuck. We're innovating and making real progress. Collaboration and fresh thinking led to an elegant solution. It inspires the next generation to see nuclear science as a field of opportunity. Better waste solutions mean more options for clean, reliable energy. The promise of advanced, safer reactors feels closer than ever. Science is building a foundation for a sustainable energy future. The future of nuclear energy is brighter, and that's something to celebrate.